Imagine standing at the edge of a coastline, staring out across a vast stretch of dark, churning water. The wind whips off the surface, carrying with it the salt and spray of a sea that has separated two pieces of land for thousands of years. Beneath your feet, the bedrock descends sharply into the ocean floor, a landscape of mud, shifting sands, and crushing pressure that no human being was ever meant to inhabit. And yet, somewhere beneath that water, hundreds of meters down, in conditions that would destroy ordinary construction equipment in hours, thousands of workers are drilling, blasting, and assembling one of the most extraordinary feats of civil engineering ever attempted. You won't see it from here, you won't feel it, but it is happening right now, beneath the waves. This is the world of China's undersea tunnels megaprojects, so ambitious, so technically complex, and so staggeringly large that when American engineers first reviewed the construction plans, many of them simply refused to believe the timelines were real. These are tunnels stretching over 5,000 meters beneath open ocean. Some of them span more than 10 kilometers from portal to portal. They carry high-speed trains, 6-lane highways, and millions of passengers every year through a geological environment that engineers have described, without exaggeration, as one of the most hostile places on Earth. So how did China build them? How do you drill through the seafloor without the ocean pouring in and killing everyone inside? How do you maintain millimeter-level precision in a tunnel buried under hundreds of meters of water and rock? And how do you do all of it faster, cheaper, and on a scale that no other nation has matched in the modern era? Those are the questions that have kept engineers on the other side of the world awake at night. And today, we're going to answer them. To understand what makes China's undersea tunnels so remarkable, you first need to understand the sheer scale of what has been built. The Xiamen Xiang'an subsea tunnel, completed in 2010, stretches for 6.05 kilometers beneath the Taiwan Strait, the longest undersea road tunnel in China at the time of its opening. Then came the Qingdao Jiaozhou Bay tunnel, piercing beneath a major bay for nearly 7 kilometers and carrying 6 lanes of traffic to connect a city that had been divided by water for generations. But perhaps the most jaw-dropping of all is the Jiaozhou Bay tunnel and the series of deep-sea rail tunnels now threading beneath the South China Sea corridors, some of which extend beyond 5,000 meters of continuous undersea passage. When you add portal approaches, service tunnels, and emergency infrastructure, the total excavated length in many projects exceeds 15 kilometers of underground construction. These numbers are not just impressive on paper. They represent engineering challenges that begin long before a single drill bit touches the seafloor. The first and most fundamental problem is geological uncertainty. The ocean floor is not stable, homogeneous rock. Beneath the bays and straits of coastal China lies a complex patchwork of fault zones, soft marine sediment, ancient volcanic intrusions, and water-saturated rock formations. Drive a drill into the wrong layer, apply the wrong amount of pressure, or miscalculate the permeability of a rock face, and you don't get a setback. You get a catastrophic inrush of seawater at pressures that can collapse a tunnel boring machine in seconds. The Chinese response to this challenge was methodical and relentless. Before a single meter of tunnel was dug in any of these projects, survey teams spent years, not months, years conducting seismic reflection surveys, deep core drilling, and three-dimensional geological modeling of the seafloor. In the case of the Jiaozhou Bay project, engineers identified no fewer than 36 distinct geological fault zones along the planned alignment. Each one required an individual engineering solution, not a general strategy, an individual solution. That level of precision in pre-construction surveying is what separates a successful undersea tunnel from a disaster, and it's one of the first things that surprised Western observers when they examined Chinese project documentation. With the geology understood, the next challenge was deciding how to actually excavate the tunnel. China employs two primary methods depending on depth, rock quality, and project timelines. The first is drill and blast, a technique as old as modern mining, but radically refined for marine tunnel applications. In this method, workers advance the tunnel face in carefully controlled stages, drilling precise patterns of boreholes into the rock ahead of them, inserting explosive charges, detonating them in sequenced microblasts that fracture the rock without destabilizing the surrounding material, and then clearing the debris by an army of mucking machines before repeating the cycle. The key word in all of that is controlled. In a standard mine or road tunnel, a rough blast that cracks the surrounding rock slightly beyond the intended profile is an inconvenience. In an undersea tunnel, it can open a fracture pathway to a water-saturated fault zone. The result, engineers describe, would be uncontrolled ingress, which is the technical way of saying the sea comes in. To prevent this, Chinese tunnel engineers pioneered the use of advanced pre-grouting systems that transformed their undersea operations. Before each blast cycle, high-pressure injection probes were driven ahead of the tunnel face and filled with ultra-fine cement grout, silicate compounds, and chemical sealants that penetrate rock fractures at a microscopic level. This grouting literally sealed the rock ahead of the excavation, creating a treated zone that could withstand water infiltration even when blasting fractured the material immediately behind it. At peak operation in projects like Xiang'an, over 300 grouting boreholes were being drilled, filled, and monitored simultaneously 24 hours a day by teams working in rotation across multiple tunnel headings. But drill and blast, for all its precision, is slow, and China needed speed. That's where the second method comes in, tunnel boring machines, or TBMs, the enormous cylindrical drilling systems that look from the outside like something designed by a science fiction novelist. The TBMs deployed in China's major undersea projects are genuinely staggering pieces of machinery. These are machines 14 to 16 meters in diameter, longer than two Airbus, a 380S placed end-to-end, weighing in excess of 4,000 tons, carrying on board their own electrical systems, ventilation networks, segment assembly robots, and real-time structural monitoring arrays. The cutting head alone, the rotating disc of hardened steel teeth that grinds through rock, costs more to manufacture than most small bridges. The challenge with TBMs in undersea tunnels is not getting them started, it's keeping them alive. TBMs were originally designed for terrestrial soft ground tunneling, adapting them for sustained operation at depths where the water pressure above exceeds 40 bar, that's 40 times atmospheric pressure. Enough to crush an unprotected human body in an instant required fundamental redesigns of their sealing systems, their lubrication circuits, and critically, their maintenance protocols. When a cutter tooth wears out in a road tunnel, you stop the machine and send a worker forward to replace it. When a cutter tooth wears out under 50 meters of seawater with a fractured rock formation 6 meters ahead of the face, you cannot simply open the cutter head chamber and send someone in. Hyperbaric intervention teams, specialist workers, trained to operate in pressurized environments, wearing equipment similar to deep-sea diving apparatus, were deployed for routine maintenance on China's most demanding TBM drives. These workers spend hours in pressurized lockout chambers before they can enter the cutter head environment, and hours more decompressing afterward. It is brutal, dangerous, extraordinary work. While the machines drilled and the grouting crews sealed, the structural engineering teams were simultaneously solving the tunnel's permanent form. China standardized its undersea tunnel linings around a dual-layer system that has since become something of an industry benchmark worldwide. The primary lining is a ring of precast concrete segments, each one manufactured off-site to tolerances of less than half a millimeter, assembled inside the TBM's tail shield by robotic erectors working from computer-guided positioning systems. These segments bolt together to form a ring under compression, their joints sealed with hydrophilic gaskets that expand when wet, creating a watertight seal that actually improves with age as groundwater saturates the material. Behind this primary lining, after the TBM has passed, comes a secondary cast-in-place concrete layer that provides additional structural redundancy, houses the tunnel's drainage systems, and gives engineers a final barrier against the sea. The monitoring systems embedded in these linings represent some of the most sophisticated infrastructure sensing networks in existence. Optical fiber strain sensors, piezometers, pressure transducers, and displacement gauges are cast directly into the concrete at intervals of a few meters across the entire tunnel length. They report continuously, in real time, to monitoring centers where algorithms trained on years of structural data flag any anomaly, any microstrain, any pressure change, any suggestion of a crack propagating through the lining before it becomes visible to the naked eye, and certainly before it becomes dangerous to anyone inside. And then, after years of planning, years of drilling, Years of grouting and monitoring and hyperbaric maintenance and segment assembly in conditions that test the limits of what human engineering can endure, the breakthrough happens. The two headings meet somewhere beneath the ocean floor, their alignment confirmed by laser gyroscope guidance systems accurate to within 30 millimeters across 5 kilometers of curved undersea passage. 30 millimeters, the width of 2 fingers, across 5 kilometers of ocean floor. In the engineering world, when people say China builds differently, this is what they mean. The final fit out, installing the road surface or rail track, the ventilation systems, the fire suppression networks, the lighting and signage, and emergency refuges takes additional months. And then, one day, a ribbon is cut, a car drives through, a train passes at full speed. And on the other side, people who have spent their entire lives taking a ferry ride that could be canceled by bad weather, or a road journey that detoured hours around a body of water, step out into daylight and realize the geography of their lives has changed forever. That's what these tunnels mean. Not just the geology conquered, or the records set, or the timelines that shocked foreign observers, but the farmers, and the students, and the factory workers, and the elderly parents who can now reach the other side in minutes instead of hours. That is what infrastructure at this scale actually does. It doesn't just connect land, it connects lives. If this kind of deep dive into engineering amazes you as much as it amazes us, drop a comment below telling us which undersea tunnel you want us to cover next, or which engineering megaproject you think deserves its own episode. And if you haven't subscribed yet, do it now, because we are just getting started on China's most extraordinary construction achievements, and you do not want to miss what's coming.